hard to do that. I've taught him sit, lay, roll over, jump, go on my leg like that. He twirl like that. Yeah, twirl.
So Eleanor's going to be out today.
Sit, stay, wait.
Hey, yeah, come on in. We're going to sit either at tables or on couches or chairs. It's your call. Let's see. Drew, can you help us these things so we pick up a chair? Like maybe the dining room table chairs?
You just missed all this trick.
Put those things in the dining room table chairs.
By the strips.
Hi, Sonia.
Please?
Yes, please. Morning, Sonia.
We got a Saint Bernard.
Say it again.
We got a Saint Bernard.
I saw that you got a Saint Bernard. So cute. Oh my goodness. Yeah, she got a beautiful Saint Bernard. What's his name? Her name?
We don't have a name for him yet. We're still trying to decide. We want to call him Big Mac.
Big Mac. I like that.
Because he drools and then he shakes, and we call it the Big Mac attack.
Did you get that one from Chandler?
Yeah.
Yeah, I saw Chandler had him in her car, and she said before and after a bath. And I was wondering if it was the same one, because then I saw you guys with one, and I thought, So
Yeah, it's the same one.
Senia's moms know a friend of mine who does animal rescue. And so
We
we
work
have a big
together.
Saint Bernard. And then here, I'll put it up.
Us and Chandler all work together.
One of my favorites is that whenever you come home from a long time, almost every time he greets you,
I'll show you guys.
Howl, you'll talk.
Listen,
Every time. I'm gonna video of it.
I did.
I try to get him to sing, so whenever I say sing, he'll do a howl. Try to get him to do that. If you howl, he'll howl.
Not right now, he won't.
Won't you, Alex?
No, I'm finding her new I'm gonna show off her Saint Bernard real quick. Sonia's new baby.
Ozzy.
It's not such a baby.
Good boy, Ozzy. Good, come
on, open a page.
It's okay, it's okay.
Let's see, where did he go? She posted a picture. No, she posted, there's you. Why'd that pop up? I must have clicked it. I swear she just posted a picture. Where is it? Yeah. Okay, wait a minute. Come on, go to her page. There we go, wait a minute. Okay, where's this baby? That's a cat, that's not it. Where's the baby? I swear she posted, I know where she posted it. She posted it on my page because I shared a picture of Ozzy in my lap. This message can go away. I put a picture of Ozzy in my lap up, and then she shared, where'd it go? Oh, look at this first, guys. Look at that.
Oh my God. Oh my God.
That's you guys at our first science class years ago. I love it.
I literally remember that.
Yep.
I remember that. I remember that. Oh, wait, go back. What does that say? What does it say? Go back.
What?
Wait, it has Kermit.
It says, I'm not surprised. I wouldn't even be surprised if the dinosaurs returned at this point, because it's crazy right now. Like, the world is crazy.
Wait, no, go back.
No. I'm looking for, here we go. Okay, wait. There he is. Is that your baby?
Yes.
That's Senya's new baby. Isn't he cute? Oh my goodness. He's so big. Hey, what's up, Sky?
He's 71 pounds.
71 pounds? Are you further from your microphone, or are you on a different device? You're harder to hear today.
He's 71 pounds and he's 4.5 months.
71 pounds and he's 4.5 months. That's gonna be something.
That's a big boy.
Yep, that is a big boy.
Good boy. Ozzy. Ella's next to get.
200 pounds.
All right, well, after these, I think we've got everybody.
What is it? What is it, Lovey? Hold on. Guaranteed to go help.
Sorry. What now, dear?
Guaranteed to go help.
No, we're not gonna do that. That's still working.
Yeah, every time You should get every time you come home.
Okay.
It's like,
Have I got Jocelyn over here?
Your mom has a video of it. No, she just cast it either like a giant golden retriever or like a little teacup dog.
Hmm.
You should get. Yeah, you should get. If you're gonna get a golden retriever,
What?
I might as well.
Just want to see, do I have Jocelyn yet?
German Shepherd.
It's the first dog I'm ever gonna get.
Mhm.
German Shepherd?
Nope, I don't see her.
If
Then I'm getting a golden retriever.
I'm getting.
And then
Golden retrievers
All right, well, we can come back to it.
Retrievers are
Okay, gang, so I think the 6 of you here today are all that are going to be here today. And Eleanor will get online at some point, and Jocelyn. Oh,
Laura entered the waiting room.
did she just now?
Danny.
Eleanor did?
And I was thinking, like,
Oh, yep, she just did.
either a police or a military have dogs.
Danny.
Yes.
He'll get up to
Hold on a second. Hold on a second. It's hard to hear Senya today, so hang on, y'all. Drew, shh. It's hard to hear Senya today. She's trying to talk to me. I can't hear her. What'd you say, sweetie?
Our Saint Bernard is gonna get up to 200 pounds.
The Saint Bernard will get up to 200 pounds.
And he also likes our golden retriever and 2 German shepherds and 2 corgis.
Wow. She has a lot of animals. Okay, wait. How many total animals do you have? She's thinking.
24.
24? Are you for real? She has 24. So I was going to say, does anybody have more than that? But I don't even think we need to go there. I think she wins.
I have 500 ants.
500 ants. Okay, you could win that way.
Maybe spiders too.
We've got, the dog, my mom's dog, and the fish. But, I moved the fish, so I would remember to clean him today.
No, we have creeks and we get minnows.
Danny.
Yeah, we have.
Yes, ma'am.
Creek, we get
We have
salamanders.
6 cats, 6 dogs, and 2 guinea pigs.
Yeah. You guys.
Hang on a second. She said something else. She's hard to hear today. What'd you say? 2 guinea pigs and what?
2 guinea pigs, 6 dogs, and 16 cats.
2 guinea pigs, 6 dogs, and how many cats?
16 cats.
16.
16? That's crazy. I was gonna say that's ridiculous, but I won't say it. When your mom's a vet, I guess you can manage. All right, let's start going, guys. Okay, so I'm gonna, Drew, I need you to stop talking. So I am going to put on my screen share, so you girls will be seeing what everybody else is seeing up on the TV. So there we are. And I have a slideshow for you guys today. Now, our lab today is, that's the wrong one. Why is it there? Our lab today is going to be live streamed. So it's going to take us a few minutes to set up, but if the 2 of you come back at 11 for the link for the lab, we're going to live stream the whole lab straight to Zoom, and then Zoom will live stream it to our Facebook page all at the same time. So like anybody that wants to join us can join us.
So, when is it gonna end?
The lab shouldn't take too long. Hopefully, maybe, well, it depends on how much fun we have. We can do it in 30, 40 minutes. We might take a little longer just because it's fun.
My mom, she has to leave to go somewhere at 10:30. I might have to stay home and babysit my sisters.
Okay.
Either way, I can either stay here or go with her.
Okay. Yep. And you can always watch it later too. So, all right. So let's go ahead and start with today's lesson. So you guys need your books out to make sure that we cover everything that's in there. And I'm going to pass out homework that I have graded. That's Eleanor. She's not here.
So we're doing lab 5.
Eleanor's still not here. Drew, this is you. Whoops. I'm dancing around Lily. There you go, Drew. That's you. Jules, that's more you. Some more Eleanor. Okay, and that's what I have. Yours all went back electronically and stuff because your mom sent it. So you send it electronically. I try to send it back electronically. Yep. Excellent. All right. So today we're going to talk about the last bit of changes in matter, and this is wrapping up Unit 1. So what's that mean if we wrap up a unit?
Test.
Yep, a test. Right. We will be having a test at some point.
Is there any questions worth more?
I can look for you.
You know what
when we're done.
questions there are?
Yeah, I'll have to go back and look when we're done. Remind me towards the end of the lesson and I'll pull that up. All right, so
Did you get the pictures I sent in last night?
probably, yeah, I got a bunch of stuff last night, but I have to shift it all to another file so I can grade it. And I didn't start that yet this morning because I was busy setting up lab. All right, so here we go.
Okay.
Physical changes. All right, if we're talking about physical changes, here are some examples, okay? So crushing a can. How is crushing a can a good example of a physical change?
You can get it back. You can just straighten it back out.
Right.
You can't, it's harder though.
You can, but yeah,
You can technically, but-
It would do the time to do that.
but you could. It doesn't fundamentally change the substance of the can, does it? No, not really. Okay, and chopping wood, right? You could glue it, but you're not fundamentally changing the substance of the wood or the characteristics of the wood. Wood is still wood, right?
Can you technically not-
Exactly.
You can even kind of learn that thing with the axe.
You could cut logs like that
You use a sledgehammer at the ledge or just.
with an awl. Yeah, it depends on how big the
Yeah.
yeah.
Some just use a sledgehammer, so you can keep yours.
right.
My dad just makes it.
So breaking glass is another example. That's really hard to put back together. So putting back together is a difficult way to go about it. But you could say that the glass isn't fundamentally changed if it's broken, right? And dissolving sugar in water. Now, if you remember, we did dissolved salts in water for our separating mixtures, right? And they came right back out like salts. We didn't change them chemically. We didn't fundamentally change the substance.
Right.
Boiling water, obviously, because now you're just changing state, right? You're going from what?
A liquid to a gas.
Yeah, liquid to a gas, right. Sublimation of dry ice. Do you remember what sublimation is?
I mean, it gets larger.
Anybody know what was sublimation? So oh yes, what you got? Sunny raised her hand. Oh, hang on, you're muted. Let me unmute you. Oop.
Should we be in our binder?
Would the sublimation be in your binder?
Yes. Would
I
it be
don't
in?
know. I'm not sure if it would be. I think it isn't. So I'm wondering if anybody's heard it. Okay, so sublimation is a change of state where you go from a solid to a gas without going to a liquid first.
I thought it was vaporization.
So no, well, vaporization is a type of sublimation. So if you have, say, dry ice. Do you guys know what dry ice is? It's
Yes.
a solid, right? And when it gets warm,
Yeah, it's in the glossary back here.
in the glossary. So Alec found it in the glossary.
It's very, very dangerous.
Dry ice goes from a solid block to gas, and it doesn't turn into liquid carbon dioxide first, because that's what dry ice is, right? It's carbon dioxide that's been cooled to the point of being a solid. Did you lose something, Jules? Are you okay?
Yeah,
She's wondering what page.
We're just kind of in general. We're not on a page right now. You're good.
Ice up pretty fast to make it.
Mm-hmm. Now, I want you guys to know this. I remind people of this every time I talk about sublimation. But I guarantee you, the first time it snows, there will be a YouTube genius who produces a video of a snowball and a lighter. You seen these? They will light the snowball and then they'll go, look, it's not turning into water. It's turning black. It's plastic snow. The government conspiracy. It's the craziest thing because it happens every year. It's always some new YouTube genius. All they're doing is getting the snow so hot that it's sublimating. So you're not seeing it melt because it's turning directly into water vapor. And the black stuff is the soot produced by the butane in the lighter.
Yeah.
They're not burning the snow as they think they are.
Oh my
I
God, I'm a
promise
genius.
you.
can burn
I
snow.
promise you, it's the first time it snows this year, go looking for it. You will find one of these geniuses.
What if you just snow on the table, see what happens?
Yeah,
What if it
yeah,
doesn't snow?
yeah, it'll melt if you stick it on the table.
It's
So.
probably not gonna snow. We have freaking 3 months
No, it's not. A lot of people are
left
saying
in
it's
this
gonna snow.
year.
So mixing sand with water, that's an obvious one, right? And shredding paper, that's kind of like breaking glass, same idea. Melting an ice cube, here we have 2 different changes of state with water, right? And then mixing red and green marbles is a good example of a mixture. What kind of mixture would mixing green and red marbles be? Heterogeneous mixture. Okay, and how about dissolving the sugar in the water?
Homogeneous.
Yep, homogeneous. Very good. All right, you got it. All right, so how about some chemical changes? Let's see. Cooking an egg. How is cooking an egg a chemical change?
Because it changes the.
Yeah, it's edible. It fundamentally changes the substance, right? Raw egg and cooked egg are not the same.
Totally different. You can eat
Yep.
the cooked egg, but the raw egg you'll get very, 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 very,
They're
very.
all so quiet today. Hold on one second. I'm seeing if there's I don't know why y'all are quiet. One sec. It's weird. You guys are like extra quiet today, and I don't know why. I'm thinking it's me.
See if you can just change it to the speaker.
Well, no, it won't change to this speaker. But this one should be, see this all the way up.
Put the digital output.
You know what? Let me make sure my Bluetooth isn't. Oh, wait. There. That should help. One of y'all say something.
Hi.
That's a little better. I don't know. It's being weird.
It helps me when I turn my volume up if my volume wasn't all the way up.
Well, it's all right. We'll figure it out. So yeah, we said cooking an egg and vinegar and baking soda. What happens when you do that? Yeah. Ella's got it. Yeah, it does. It blows up, right? It makes bubbles and it foams. So anytime we'll find this out, we'll get to acids and bases, but vinegar is an acid, baking soda is a base. And when you mix an acid and a base, you end up producing a salt, a water, and a gas. So you get salt, water, and gas, some kind of a salt. And the gas is the most obvious thing when you do vinegar and baking soda because you see the bubbling take place right in front of your eyes, right? Yes.
Oh,
I mean, we could try that. I'll try that. Hold on, Alex has a TV suggestion. It didn't used to automatically hook up like that, but Jason's always messing with it, so that's possible. It's up. No, it's up. The volume's up, so that's not it. But, Alexa, never mind, cancel Alexa. I don't know. He's automated everything now, and it's confusing. All right, how about this one? Electroplating. Do you guys know what that is? You ever see stuff that says like it's silver plated or gold plated? You ever seen that? Sometimes you'll see jewelry or something, or a coin even, and it'll be plated in a metal. They use a process with electricity where they cause the silver or gold or whatever they're putting on the outside to adhere to the metal beneath. And burning wood, obviously, because we produce gas and we produce soot.
I thought you said burning England at first.
Burning England? No.
You said it fast.
Fireworks. Now, this is the closest thing to what we're going to do today. So you guys have seen all the different colors in fireworks, right? There's green, red.
I mean, I haven't seen purple in fireworks.
You haven't seen purple?
No.
I've seen it occasionally. I'm impressed with the ones that spell things or make shapes. That's amazing to me that they figured that out. But the colors are actually pretty simple. So today, I'm sorry, I swallowed my own air bubble. Today in lab, we're going to basically make colored flames the same way they do colored fireworks. All right, how about rotting bananas? Rotting bananas and apples and fruit like that, that's oxidation. That's oxygen in the air reacting with a chemical in the fruit that causes it to brown like that. And that's no good for you, but necessary if it were to fall on the ground in the woods. Like if it fell on the ground in the jungle and it never rotted, that would be pointless, right?
It'd be a plastic banana because bananas can't stay ripe forever.
Banana. It would be a plastic banana, she says. So
Bunch of people get killed because they're putting plastic bananas in the trees.
Yeah, that's right, bananas in the trees. So this, I actually found this. This is an old nail or a bolt or something that was in a creek near like a really old structure. So then this now, because it's covered in rust. No, this wasn't.
That one was.
No, it wasn't. I know where I got it. And you didn't find that one. I found that one. Drew, stop arguing. Anyway, if you find a nail that's rusty, even if it's not that rusty and not caked on, just a little bit of rust, it's going to weigh more than the original nail because the reaction that causes the rust involves oxygen combining with the iron. So then what you get is more mass on that nail because now you've got the oxygen combined with it. So rusty nails weigh more, even though they're not necessarily what you want to be using, right? Chemical batteries. So when you use any kind of chemical battery, Those, they call them dry cells very often. Sometimes there are wet cells. It's a different kind of battery, but the kind that you're familiar with that you use in toys or devices or whatever, those are
Blackout.
dry cells. Yeah. And then metabolism. Metabolism, those are the chemical reactions that occur in your own body that help you to digest your food, run your internal engine, essentially. Right?
Oh.
Great. Yeah. So those are all chemical reactions. So when learning about chemical reactions, it's important to remember this law. Matter is never created or destroyed. What law is that? Matter is
That is a conservation of matter.
Yep, law of conservation of matter. Good job, Drew. So always remember that matter is never created nor destroyed. Excellent. All right, how about, so matter is anything that has mass and takes up space, right? So the law of conservation of matter says that matter is never created or destroyed. And matter is anything that has mass and takes up space. Then the law that applies to chemical reactions is in a chemical reaction, mass is neither created or destroyed. So what's this one called?
Law of conservation of matter.
Yeah, law of conservation of mass. Good job. So matter's never created or destroyed. It can only change form. Same thing with matter, right? And the reason that's true for mass is because it's true for matter. You can't have one without the other.
How is something destroy matter with some big moons and stars? No. Something with a neutron star.
Something with a neutron star to do what? I couldn't.
To destroy matter.
To destroy matter.
It's still always
No,
gonna
it
be
would
there.
be there. It would just kaboom elsewhere. All right, so in a chemical reaction, you've got chemical bonds, which we're going to start talking more about really soon. The chemical bonds are either broken or formed in a chemical reaction. That's what's happening. So if you break a bond, it's going to require energy to break. And if you form a bond, it's going to release energy when it forms. And so if your energy is absorbed by a reaction versus if your energy is released by a reaction. So let's think about it. If we're breaking a bond, it's requiring energy, it's absorbing it. Or if we're forming a bond, it's releasing. Here is energy in the form of heat, okay? And so if you're putting energy in, okay, then what you're getting here is an endothermic reaction. And if you're releasing energy, you're getting an exothermic reaction. So what happens is if you're absorbing energy into the reaction, okay, absorbing the energy, you're breaking a bond. Energy is going in, it's going to feel colder than the surroundings, okay? Versus if you're releasing energy, okay, and energy is coming out, it's going to feel hotter than the surroundings. Does that make sense at all? So if you touch the bathroom floor, how does it feel in relation to your hand as far as temperature goes? Cold, right? But the bathroom floor is really the same temperature as the air. It's your body that's warmer, and the floor is just a better conductor, the tile is. So when you touch it, it's actually taking the heat from your hand and pulling it out into the floor, because heat always travels from warmer to cooler, okay? So your book also talked a little bit about heat and temperature too, and I think I put a slide in here for that, but it got a little wonky. So we're gonna make sure we clear that up. So this was in your notes, right?
Yes.
So what did you get as the definition for temperature? Is your hand up, Senya, or was it just up from before?
It was just up from before.
Okay, cool. We got C. So temperature is a measure of the energy of motion of the particles in matter. Correct. So temperature is about kinetic energy. Okay, kinetic is energy in what? What's kinetic energy? What kind of energy is it? Who did physical science last year? Energy is what's kinetic energy? What kind of energy? It's energy from motion. It's energy in motion. So like when a car is rolling, it has kinetic energy. When it's stopped at the top of a hill, it has potential energy because it's going to go down soon, right? So temperature is about kinetic energy, and it's a measure of how fast the particles within a substance are moving. Heat is how that energy is being transferred from one object to another. So temperature is about the measure of how things are moving, and heat is about how the temperature is being transferred. Does that make sense? So what you, oh, sorry, I clicked it already. F, exothermic change is the change in which energy is released. Okay, so what'd you get for 8? A, chemical energy, energy that's stored in chemical bonds between atoms. Very good. B, endothermic change, change where energy is absorbed. Good job. What do we get for number 10? D, thermal energy, the total energy of all the particles in an object. Very good. Also, when you're looking at thermal energy here, it's the total energy of all the particles in an object. How is that different from temperature? Temperature is the average measure of the motion. So total versus average. You guys know how to get an average?
Yes,
Yeah, add up all the different things and divide it by the number of things. Yep, okay. So what about 11? What's the law of conservation of mass? E, the fact that matter is neither created nor destroyed in any physical or chemical change. Very good. How about 12? H, a physical change alters the form or appearance of matter but does not turn the substance into another substance. Perfect. And 13 would be G, a change in matter that produces one or more new substances. Very good.
All right.
You got them all right? Good job. All right, so here is your thermal energy versus temperature versus heat graphic. All right, so your thermal energy is the total energy of all the particles in a substance, right? And like I said, your temperature is the measure of the average kinetic energy of all the particles in an object. And the heat would be the transfer of that energy, okay?
Am I supposed to
So
have
when you write about thermal, what'd you say, Sonia?
Am I supposed to have that in my book? In
Nope.
my binder?
Nope, I just have it for you to see.
Okay.
So thermal energy is expressed in joules. That's how we measure it, in joules, okay? Not joules like you, joules with an O in it. Did you know that? Joules is a thing? Yeah, joules are, yep. You know what, well, when you do physical science, if you do physical science with me, there's a lot of talk about joules. Temperature we express in degrees, like Fahrenheit, Celsius, Kelvin, right? And then heat is also in joules or also in calories. Now, when you look at something that you're eating and you read, like, what's on your bottle there? How many calories is in that?
5 calories.
5 calories. Okay. 5 calories in Lily's bottle of whatever that, what is that?
Sparkling ice.
Okay. Ice. It's what flavor is it? Fruit punch flavored ice drink. Okay.
Sucralose for less calories or something.
You use what? Sucrose?
I think
Yeah.
you use sucralose.
Sucralose, right.
It should be more calories.
That's true, yes. So calories are a measure of heat too. And think about this. When your body metabolizes things, it produces heat, okay? So basically that's telling you how much energy in the form of heat you would be taking in and able to put back out. So anytime you produce heat constantly, even sitting still, even sleeping, right? But if you start running, do you produce more heat? I mean, yeah, heck yeah, right? All right, and then lastly, your thermal energy is going to vary with mass and temperature. Your temperature doesn't vary according to mass, and then your heat varies with mass, specific heat capacity, temperature, and change of a substance. I don't want you to worry as much about the third row there as much as the top 2, just to give you an idea, to make sure that it's clear. All right, so let's look at this part of your homework, understanding main ideas. Let's make sure everybody gets that out. I'll give you a chance to get that open. You have your homework out, Drew? Yep. You got it out, Alex? You can check them? Let's check over them. Make sure that we can check over them. All right. Hey, Ozzy. Aw. All right. So what do we get for number 1? Is this going to be a physical change, a chemical change, or both a physical and chemical change? Both. Ella says both. Anybody disagree with Ella, or does everybody all think it's both? Both? Okay, yeah, great. Can somebody give me an example of a physical change that occurs when energy is added or removed?
A light bulb.
A light bulb.
It'll go on when you add energy, off when you take it.
Ms. Harderwin, what'd you say? How about, think about water. Drew, what you got?
Oh, mine wasn't water, but
What?
I connect the energy to glass to making it break.
Adding energy to glass so that it glows. That's kind of like the way, so that it breaks. Okay, yeah, all right, there you go. So that it breaks. All right. So if you take a glass and you smash it with a hammer, you've just added some energy, right? You've added kinetic energy as it hits it, and that would break it, and that would cause a physical change because that would be broken glass. Or if you throw a baseball at a window, right? Same idea. What's an example of a chemical change where energy is added or removed? Can anybody think of one? Drew, you got one?
Like when you heat up water.
That's a physical one, when you heat up water. Because it's going to go from...
When you turn on a
When you turn on what? What'd you say, Sonia?
microphone,
When you turn on a microphone? Oh. No, that's electricity. That's kind of, do you have one? Cooking an egg. That's a good example. Okay, so cooking an egg. Yeah, okay. Slime, does it get warm or cold when you work with it? It gets a little different, doesn't it? Yep. Making slime. There you go. That's a good example too. So sometimes the change in temperature is so small that you don't realize it, but it does happen. You may not recognize it because it may not be, your hands might not be sensitive enough. But if you had a sensitive enough thermometer, you could definitely, or temperature probe of some kind. So when you produce a new substance, what's this an example of? Right on. Yeah, everybody agrees. That's chemical. Very good. What's an example? One of you girls have an example of a chemical reaction? A chemical change? She's thinking. They're both thinking really hard. Chemical change. Can you think of one? Ah, I put them on the spot. Did any of you have one? Can you think of one? A chemical change?
Putting chlorine into a pool.
Putting chlorine into a pool. That actually does. There are some chemical reactions that occur, yeah, with some other things in the water.
Because like, when you first open your pool after the winter, they put so much chlorine in it. It's like a bog, kind of. It's green, it's foggy, you can't see the bottom.
So she says if you, when you open your pool for the first time after the winter, they put a lot of chlorine in it. Sometimes they call that shocking the pool. But she says it can turn green and it gets all like fizzy and weird and foggy looking.
Because we have a pool and when we opened it and they put so much chlorine in it, it was very green. Yeah,
she said they put so much chlorine in it that it was very, very clean. So that's good to know.
Green and clean.
What you got, Sonia?
Like if you had a lid over something and then you opened it and get steam everywhere, maybe?
If you had what open?
Like if you had steam inside a pan and then you let it out, it would go everywhere.
Oh yeah, that's more like a physical one. So if you have steam, well that's more about pressure. So say you had a pan with a lid on it and you were heating it up and you took the lid off and the steam went everywhere, right? So what you've done then is you've suddenly decreased the pressure that water vapor and steam was being held within. So it's a gas, and a gas is going, because gases don't have a definite volume, right? So it's going to spread out as soon as you release the pressure.
What about like melting wax?
Melting wax. Okay, so if you're melting wax with a candle that's burning a flame, you have both chemical and physical going on, because the physical is the melting of the wax, but the wax, the oil in the wax is actually feeding the fire. So that part, the fire is burning that oil. So that part is chemical. So you have a little of both going on.
That's why you have to blow out the candle instead of just letting it burn out.
Yeah, blow them out, just letting them burn forever.
You can let it burn out depending on the size of the candle, but sometimes it's not safe to just let it go on during the night.
Yeah, because they'll just burn down to nothing, right?
And then you can also accidentally set your house on fire.
Yeah, it can set your house on fire. When my grandfather was, after my grandfather passed away and we were all clearing out his house, there was a candle burning on, it was on top of that radio out there in the hallway, which was his radio. And for whatever reason, I guess it had burned down, like you're saying, really low, because we weren't paying attention. We were packing boxes. And it burned so low that it got the glass so hot that the glass just exploded. And we were all in another room and we heard this bang, and we all go in there and there's like wax and glass everywhere. And yep, it was a big mess. Do you know what? Okay, I'll tell you, I think I shared this with some of y'all last year. So this is interesting. House fires, like Jocelyn was mentioning, candles can cause house fires. So my brother-in-law is a battalion chief in Virginia Beach. So he's a firefighter and been for years. He just got promoted to battalion chief, which was a big deal. So we were all very excited. But anyway, he told me something the last time I saw him that I had never heard before. You know the little fans in your bathroom that you turn on?
Yeah.
They're usually noisy and obnoxious. Okay. Pardon the vulgarity, but he calls them fart fans. I didn't know there was a word for them. It makes sense because you turn them on when the bathroom smells bad, you know? He said those cause tons of house fires because the little motor inside is not meant to run. And people turn them on,
can overheat.
out of the bathroom and forget about it. And then the motor overheat. And it causes a fire. What'd you say?
I was saying what you were saying. It can overheat.
Yep, it overheats. And the little motors cause fires. But he says all the time they will pull up to a fire and they'll be like, all right, who thinks before we go in? They sometimes firefighters do crazy things because their job's hard, so they look for levity. So they do stuff like bet on what started this fire. You know, someone's house is burned down, but they're betting on what started the fire because they still have to do their job. It's a hard job.
We have a timer on this.
Do you?
They just want to try and make their job fun.
They bet on whether or not it was a fart fan that caused the fire. It was a fire. So that's one of the things
to make their job fun.
Yep. It's an important job, man. All right, so how about a substance changes form, but it remains the same substance?
Physical.
There you go. Yep, that's a physical one. Jocelyn got that one. There we go. So that would be like any of the examples we talked about in the first slide with all the
crushing a can.
Glass. Yep.
Evaporating water.
Evaporating water. Yep.
Ripping up paper.
Ripping up paper. She's just laying them out here. I love it.
Coloring a picture.
Coloring a picture. How about freezing water? That one's easy. Physical. Right. Very good. And rusting metal. Chemical. All right. Now, I want to show you guys this video, but it's, for whatever reason, it did not want to play. Let me see if it will. Yeah, good. It's going to. Now, this may not do what I want it to do because y'all may not be able to hear it.
Accepted by the scientific
here we go. Hang on. It started late.
Advancement would not.
All right. Here we go.
What do an ancient Greek philosopher and a 19th century Quaker have in common with Nobel Prize winning scientists? Although they are separated over 2,400 years of history, each of them contributed to answering the eternal question, what is stuff made of? It was around 440 BCE that Democritus first proposed that everything in the world was made up of tiny particles surrounded by empty space. And he even speculated that they vary in size and shape depending on the substance they compose. He called these particles atomos, Greek for indivisible. His ideas were opposed by the more popular philosophers of his day. Aristotle, for instance, disagreed completely, stating instead that matter was made of 4 elements: earth, wind, water, and fire. And most later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory. Whereas Democritus's atomism had been purely theoretical, Dalton showed that common substances always broke down into the same elements in the same proportions. He concluded that the various compounds were combinations of atoms of different elements, each of a particular size and mass, that could neither be created nor destroyed. Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist J.J. Thomson's 1897 discovery of the electron. In what we might call the chocolate chip cookie model of the atom, he showed atoms as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom didn't stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small, positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atom's thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that the foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from the dense, positively charged nucleus. But the atomic theory wasn't complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model. Drawing on earlier work by Max Planck and Albert Einstein, he stipulated that electrons orbit the nucleus at fixed energies and distances, able to jump from one level to another, but not to exist in the space between. Bohr's planetary model took center stage, but soon it too encountered some complications. Experiments have shown that rather than simply being discrete particles, electrons simultaneously behaved like waves, not being confined to a particular point in space. And in formulating his famous uncertainty principle, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they moved around an atom. The idea that electrons cannot be pinpointed but exist within a range of possible locations gave rise to the current quantum model of the atom, a fascinating theory with a whole new set of complexities whose implications have yet to be fully grasped. Even though our understanding of atoms keeps changing, the basic fact of atoms remains. So let's celebrate the triumph of atomic theory with some fireworks. As electrons circling an atom shift between energy levels, they absorb or release energy in the form of specific wavelengths of light, resulting in all the marvelous colors we see. And we can imagine Democritus watching from somewhere, satisfied that over 2 millennia later, he turned out to have been right all along.
Oh, there we go. So here's the thing I want you to think about today during lab. So this is back to being more like a simple Bohr model. Remember, Bohr said that your electrons circle your nucleus at these fixed intervals, right? Kind of like ripples in a pond. Very much.
Just ask me what you'd like me to do.
Oh,
Shut up.
Alexa, hush, I'm not talking to her. Anyway, you got your nucleus at the middle, and then you have level K, L, M, N, and they go on. And each level can hold a certain number of electrons. So you can get 2 in this level, 8 here, 18 here, 32 here. While that's kind of true, it's definitely pretty much true about how many you can hold at various energy levels. The energy levels are not these perfect little shells or rings. So if you were to imagine this 3D, it would be like an everlasting gobstopper, right? You ever had one of those? We have like layers and layers and layers that build on. Okay, same idea. Yes, Sanya? Nope, she froze from, there she is. Did you have a question?
Yes, I was gonna ask, will our lab thing start at 11?
Yeah, 11, because I need a little time to set up. But it'll be on the Facebook page, and it'll be recorded too. So you can always just watch it later if you don't catch it live. So here's the thing to remember. When we talked about chemical reactions absorbing and releasing energy, the same thing happens when electrons move. So electrons are always wanting to be at their ground state. So if we start here, you see how you have all these levels out here? An electron does not want to be, say you have like hydrogen, okay? Your one electron of hydrogen does not want to be out here. It wants to be at the lowest possible energy level. So if an electron moves to a higher level, they call that an excited state. And there are some things that can make it do that. Heating it up really fast with fire will do that. You split the atom. You split the atom, basically. You split the nucleus, which is not what we're going to do. So anyway, that causes it to absorb energy because it's now become very excited. It's increased its energy. When it drops back down, it's going to release the energy when it goes back to its ground state. So today, when we take our chemicals and put them on the flame, it's going to send electrons in some of the atoms up an energy level. They're going to absorb energy. And then when that particular atom cools down, which is going to happen rapidly, right? Because there's going to be a bunch of them. It's going to release energy as it comes back to its ground state. And it's going to release it as light. And you're going to see it as a different color of light, which is super cool. So we've got about 17 minutes, which is going to give me time to, I have to set up the lab. It's going to take me a few minutes because I have to move my computer and then get all the streaming hooked up because that takes just a minute. But does anybody have a question about today's lesson? Are we all good? You had a question about the test, right? Yes. Which question, Zenia?
Here's one. Is it okay if I just watch the video after?
Of course.
On Facebook. And also, is it this week or next week we're gonna cause I don't know if the Rico thingy. My mom wanted to know about the Rico thingy, if we're doing it today or tomorrow.
Oh, you can always send Rico in. Even if your homework is keep in binder, you can always send Rico in. So Nope. All right, so what I'm gonna do is I'm gonna turn off this on the TV real quick because I don't want to share that screen because I'm gonna open my grading app real fast. And I will tell y'all how many questions are on the test. So ladies there, just hold on a sec, and everybody else here. All right, so, and I can probably tell you what to look over real fast. Well, there's probably some of each, so let me see. Chapter 2, oh, that's the other class. I'm like, what? Here you are. All right, so your Unit 2 test is going to have 1, 2, 3, 4, 5, 6, 7 multiple choice, 2 short answer, and 2 true or false for a total of 12 questions worth 19 points. So if you have pen and paper, here's what you need to write. You need to study your SI unit for mass. You need to know what that is, which should be easy. SI unit for mass. You need to know about the formula for density. Yep, density. You need to know the formula for a volume of a rectangle.
Formula for what?
Volume of a rectangle. And remember, this is recorded and will be on YouTube later tonight. So if you don't get all this written down, you can go back and watch this part of the video, right? This class. Yep. You need to be able to identify a physical change out of some options. You're going to have to explain law of conservation of mass. You're going to need to, found a typo. 1 second there. You're going to need to talk about describing how something is a chemical change, a physical change, not a chemical change. Like, be able to define between the two. Give examples of chemical properties. Be able to identify which is a pure substance. It's not as hard as you think it is. It really isn't. You're going to have to describe which, there will be a list of methods, say which one can't be used to separate mixtures. You're going to have some definitions and term matching. You're going to need to be able to understand the definition of temperature. And lastly, know about exothermic versus endothermic. And that is it. So if you guys can study over that, everything we've gone over. There's nothing on the test that we haven't gone over. Some of it's thinking questions, but it's all stuff we've gone over. So you can always go back and watch the end of this. Okay? All right, we got to get setting lab up. So see you back at our 11 or not see you back at 11, doesn't matter. Okay? All right, guys. Tell girls goodbye. Bye, girls. Wave at them. Turn around. They're behind you. Bye, girls. All right. See y'all in a bit.